Hey, AP Chem, welcome to Chapter 5, Part 5. So we're going to talk through the next couple concepts. And the first one we're going to talk about is mole fraction. So you already know what a mole fraction is. Let's just review that quickly. So mole fraction is represented by chi, and it's going to be a part of what you're looking at over the whole, like all fractions or percentages are, right? It's a part out of a whole. And usually when we're talking about mole fractions, we're talking about a solution or a mixture. And that's what we're talking about here also. It's a solution or a mixture of gases specifically. And so your part is going to be one gas. And remember, mole fraction is in moles. So it's the moles of one specific gas over the moles of all gas. So you can represent that as moles total, or let's just skip this word. If you have the moles of one specific gas, you can have the moles total written like this. Moles of gas A, moles of gas B, moles of gas C, and the sum of all of them. So when we apply mole fraction to the ideal gas law, notice we have that written right here. So basically, we have the ideal gas law for one thing over the ideal gas law for all things, right? So that looks like PV equals nRT for one specific gas. So that's pressure of your one specific gas. Now, volume of your one specific gas, if we have, let's say we have a flask here that's sealed off, and we have gas A, gas B, and gas C in that flask. The flask of gas, the volume of gas A by itself would be the flask. The volume of A, B, and C together would be the flask. Remember that gases expand to fit the container that they're in. And so it doesn't really matter if we have A by itself, the volume is going to be the flask. If we have all of them together, the volume is still going to be the flask. So the volume here that we're looking at is not really the volume of one specific gas. It's the volume of all the gases. So if we have part over a whole, PV equals nRT, pressure would be for one specific gas. But both of these volumes are the same because gas expands to fit its container. Okay, let's keep moving on. So moles of A, or moles of gas A, one specific gas, is going to be different than all the moles together. So, well, let's just keep going with A. R is the same, right? The R is the constant for both of them. R is the same whether you're talking about one specific gas or all the gases in the solution. And then T is temperature. And again, if we have all gases in one container, the temperature of gas A is going to be the temperature of all the gases. So temperature is consistent also. So really the only variables we have here that change for one specific gas versus the whole mixture is pressure and moles. So pressure total is going to be pressure of A plus pressure of B plus pressure of C. Remember, pressure of A is the pressure that A would exert if it was in the flask by itself, right? And then when we take the sum of these three, we get the total pressure. So down here, the pressure on the bottom would be total pressure. And then N on the other side is moles. So the total moles is going to be moles of A plus moles of B plus moles of C. So this N is also different than the N that's going to be on the top of this fraction. Okay, so we have just noticed that pressure and moles change when you're comparing one specific gas to all the gases in the mixture, but volume, the gas law constant, and temperature don't. Volume, the constant, and temperature are the same whether you're talking about one specific gas or you're talking about all the gases total. So we're going to solve this equation and push the three things that are constant all together. So let me kind of delete a lot of this writing. Poof. Let me redraw our little flask here. So we have our visual of gas A, gas B, and gas C all in our mixture. Okay, so PV equals nRT. We want all of our constants together. So we're going to move V over to the other side. So we have P equals N, and then RT over V is a constant. So we're just going to keep it over there. So that's what they've done here. They've taken RT and V and grouped them as a constant. And then what you have here is pressure and moles for one specific gas over pressure and moles total. So when you're looking at this equation, can you simplify it? Can you simplify that equation that is boxed over here in that pinkish color? And hopefully you said yes. RT over V is the same on the top and the bottom, so that actually can simplify out of the equation, and this is what we're left with. Now notice N1 over NT, the moles of part of it over the moles of the whole is what? You guessed it, it's mole fraction. And so notice that this term turns into mole fraction. And then, so we have P1 over PT equals our mole fraction. So a partial pressure over the total pressure is the same ratio as moles of one part over moles total. That's a good realization to have and kind of stick in your back pocket. And then we can kind of simplify this so we're not looking at fractions anymore. Let's just swing pressure total over to the other side. Pressure total, it reduces out here, and we're left with P partial pressure of one of our gases equals the mole fraction of that gas times the total pressure. Okay, so again, we have another relationship that we have derived out of the ideal gas law. So we've done this a couple times now. We've taken the ideal gas law, and we've derived out a couple things. The first thing that we can derive out of the ideal gas law is all the individual gas laws, Boyle's law, Charles' law, Avogadro's law, and any other combination that you want to make up. So let's say, I don't know if those actually have a name. Let's say individual relationships, or maybe like change in condition relationships, right? Because all of those really boil down to like if pressure changes, if it's initially this and finally this, what happens to volume? So you could also call them like change relationships. Okay, the second thing we derived out of the ideal gas law is the ideal gas law as it relates to density. So what was that? Pressure times molar mass over RT. Something like that. I hope that's right. Okay, and then this is the third relationship that we have derived out of the ideal gas law. So it's important for you to realize that they're all connected, relationships, it's important to realize what their foundation is. And then it's also helpful for some people to realize where it comes from, again, so you can avoid as much memorization as possible. Okay, so we're going to look at this relationship now through a couple examples. And one thing to notice here is that really you're taking a percentage of the total pressure, And that equals the partial pressure of one thing, right? It kind of gets back to this relationship here. The ratio between a partial pressure and total pressure is the same ratio between partial moles and total moles. It's the same ratio. And so you can use one to figure out the other. So let's look at one example here in the video, and then we can kind of look at some examples together in class. So, study on the effects of certain gases on plant growth requires a synthetic atmosphere composed of 1.5 mole percent of CO2. So a mole fraction for CO2 is called a mole percent. Oh, actually, that's a percent. So it'd be 1.5% CO2, which means it's 0.015 mole fraction of CO2. So this is not actually a mole fraction up here. It's a percent. It's a mole percent. Percent by mole instead of a percent by mass. Okay, anyway, moving on. 18 mole percent O2, 80.5 mole percent AR. Calculate partial pressure of O2 in the mixture if the total pressure of the atmosphere is 745 torr. Okay, let's do that first and then we'll tackle B. So partial pressure of O2. So we have a couple different, as you're solving these problems, you always want to think, okay, what do I have? And what kind of formulas or equations do I have that relates to this problem? So if you're trying to think of what kind of equations relate to this, that could be total pressure equals pressure of O2 plus pressure of CO2 plus pressure of AR. That could relate. It could also be pressure of O2 equals the mole fraction of O2 times pressure total. So after you identify kind of what equations relate to what you're given, what you want to think next is, which ones do I have? Okay, I have total pressure. So in that first equation, I definitely have one of these things, but I don't directly have any of the partial pressures. If you look on the other side, I have partial pressure of total or I have the pressure of the total again. Now I don't have mole fraction, but I do have a mole percent of O2. So I kind of do a check mark with a wiggly end to it. I kind of have this. So I'm a lot closer to the second equation than I am to the first, so I'm going to choose to use the second equation. So if my mole percent by mole of O2 is 18.0%, then my mole fraction is 0.18, my mole fraction of O2. Okay, so there I go, 0.18. Now, mole fraction doesn't really have units. We just kind of, it's like moles of your part over moles of the whole, right? So we just kind of ignore the units of mole fraction. And then your pressure total is 745 torr. So your pressure of O2 is those two things multiplied. Okay. 134.1 torr is your partial pressure of oxygen. Ta-da! We have done A. Now let's look at B. If this atmosphere is to be held in I'm going to switch colors. 120 liter space, 295 Kelvin, how many moles of O2 are needed? Okay, so again, I see volume, I see temperature. Let's take a look at equations we have that involve these things. PV equals nRT is always my first go-to. I definitely have pressure of oxygen. I also have pressure total, but they want moles of oxygen. So I need to make all these things specific to oxygen. I have pressure of oxygen. I have the volume of oxygen because it's the same as the total volume. I always have R, and I have the temperature of oxygen because it's going to be the same as the temperature of the whole mixture. So I have everything I need to use the ideal gas law here. Let's solve it for N. And then I plug in chug, 134.1. Oh, but it's in torr. Let's substitute that out. 134.1 divided by 760. All right, 0.176 atmospheres times 120 liters over 0.08. What is that one again? 0.08206. Okay. Liter atmosphere per Kelvin mole. And temperature, 295, and that is in Kelvin. Okay, let's solve this. Point 872. Okay, it should be in moles. Let's double check that it is. Atmospheres reduces, liters reduces, Kelvin reduces. I have 1 over mole. Dividing by a fraction is the same as multiplying by a reciprocal. So I do have the units of moles. There we go. And that is B. Okay, so again, just be careful that all of your variables agree. If you're talking about moles of oxygen, you should also be using pressure of oxygen. If you're talking about moles total, you should be using pressure total. Now, with that said, there's a couple different ways to go about this problem. So if you did this problem a different way than I did, that's totally fine, as long as our answers line up. All right, so we'll look at these together in class. Okay, so this brings us to the quintessential gas law experiment called collecting gas over water. This one is like the experiment for this chapter. We actually don't usually physically do this experiment. It's not in the recommended experiments from the College Board. None of the colleges actually do this experiment, but for some reason, the College Board test has really grabbed a hold of this problem, and it shows up all the time. If you go back in old tests, you'll find this problem or versions of this problem like every 3 to 5 years it pops up. So this is definitely an application of this chapter that you should know and understand and be functional in. So let's walk through it together, and then you can try some problems in class. Okay, so basically what's going on here is you have something here. Now, whether that is a powder or a liquid or a gas or something like that, it doesn't really matter what it is, as long as it decomposes under heat. So you have some type of chemical there, and then the chemical is heated, and then the chemical decomposes. So a really good reaction to use for this would involve something like baking soda. So if you take baking soda, which is sodium bicarbonate, NaHCO3, sodium bicarbonate, and you heat sodium bicarbonate, what you produce is sodium carbonate and gas. But it's not evident that you have gas right away, because the thing that forms first is carbonic acid. And so this thing decomposes into two things. It decomposes into sodium carbonate and carbonic acid. But the special thing about this reaction is the carbonic acid actually self-decomposes then. It's not a super stable compound. It falls apart into water and carbon dioxide. And so if you are to heat baking soda, what you get is this bubbling effect of gases that are being produced, and this is what it is. So we can just cross this top out. It's a really common reaction because it's cheap, it's safe, it doesn't produce anything scary, and it does something cool. And that's kind of all of the essential ingredients for an effective chemistry reaction. So it could be something like baking soda, which decomposes under heat and produces a gas. It could also be a hydrate. So if you have a hydrate, let's say you have like copper sulfate hydrate. Okay, so remember this, we talked about this before. If it's in its hydrated form, it actually forms these really pretty blue crystals. And then as it gets heated, what happens is the water gets driven off. So one of the products of this is water. And it turns into this like white powder. It's a very dramatic shift in appearance. Again, it's pretty cheap. It's fairly safe. It doesn't produce anything scary, and it does something cool. Essential ingredients for a chemical reaction. And so what you are left with is anhydrous or dehydrated copper sulfate and water, which is your gas, which bubbles out. Okay, so that is essential ingredient number one of this reaction. You have to have some compound that decomposes under heat and produces a gas. So when the gas is produced, it builds up in this chamber, and then it gets pushed out of this pipe. It gets pushed out, follows a little pipe along. We're building up pressure, and so our gas molecules are going to we're building up pressure and we're increasing in temperature. Our gas molecules are going to try and expand and fit the container, and what they find is they find an open end to this tube. And so they bubble out of the tube. Well, the tube is under a beaker, and that beaker is full of water. So remember when we talked about the barometer, how you fill the tube with mercury and then you flip it into a bowl full of mercury? Well, that's exactly what's happening here. You fill a beaker with water and then you flip it into this pool, this little pool that contains water. Okay, so as the gas bubbles up, it collects up here because the gas is less dense than the water. It's going to rise. But the gas can only collect to a certain extent, and then it's going to start pushing back on the water. And what happens as it pushes on the water is it actually pushes the water out of the cup. And so your water level, as it gets pushed out by the gas, goes down, 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 down. And you can see here in the end of our reaction, our gas has displaced the water. It's kicked the water out and displaced it. So we can actually measure how much gas was produced by the amount of water that was displaced. If you displace 100 milliliters of water, you can assume that you have produced 100 milliliters of gas. That's the volume of the gas you have produced. Okay, so that's the experiment. It's a collecting gas over water experiment. And I actually want to show this to you when we're in class tomorrow. Okay, so there's a couple considerations here to make. So in the end of this experiment, we're going to have the volume up here, whatever volume that is. Now, you may think that is the gas. Oh my gosh, just realized I wrote CO2 CO3 up here, but it's actually CO2, carbon dioxide. I hope I said that out loud. Okay, so we have a volume here, which is our volume total. But remember, our volume total is also the same as the volume of any gases that make up that body of gas. So that's really our next question. What gases are here? Let's say we do an experiment where our thing that's being decomposed produces hydrogen gas, for example. Let me erase what I have up here, and we can do that. Okay, so for example, if we combine zinc with hydrochloric acid. Okay, so this isn't exactly the same thing because it's not a decomposition reaction, but let us just ignore that for me for the time being so that I can make my point here. All right, so it's going to react to form zinc chloride and hydrogen gas. Okay, so we have a reaction going on here, and the gas that's being produced is hydrogen. So our hydrogen gas is bubbling, 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 and collecting up here. Okay, so I have hydrogen gas up here being collected. Do I have any other gas? Let's say it started as a vacuum. My reaction is proceeding, and I'm collecting hydrogen gas up there. Do I have any other gas present? I'll give you a hint. The answer is yes. What gas is it? So remember, anytime you have a liquid with a vacuum above it, that liquid, some of that liquid molecules is going to escape in the gas form and form a vapor, right? So if we're collecting this gas over water, we should have not only hydrogen inside here, but we should have some water vapor. It's going to establish itself automatically, naturally, spontaneously. We don't even need to produce it in our reaction. It's just going to come out and establish a water vapor all by itself, right? So inside this container, we do have the gas we produced, hydrogen. We also have the gas that naturally is going to establish itself above in the form of vapor, which is water. We have two gases. So this volume total is made up of hydrogen and water, but remember, gases expand to fill their container. So the partial volume of hydrogen is still the same volume, as is the volume for water. Okay, now the total pressure, however, does not work like that. So we have to take into account our two components, the partial pressure of hydrogen and the partial pressure of water, combined to make our total pressure. Same thing with moles. Our total moles is going to be, not a P. It's going to be our moles of hydrogen and our moles of water together. R is constant, and then temperature is also the same. So the temperature of the whole thing is the same as the temperature of the hydrogen gas by itself is the same as the temperature of I'm starting to write water by itself. Okay, so again, the only two that are a sum of the parts are pressure and moles, just like we saw on the last one. So in this experiment, if we collect the moles of hydrogen, we can actually calculate backwards to figure out how much of our reactants we used, as long as we have these other components. As long as we have temperature and volume, we can figure out the moles of our hydrogen gas that we produced, and also back calculate 2 moles of our reactants that we started with. Okay, so let's look at one of these problems together. Sample of KClO3 is partially decomposed according to the following reaction, producing oxygen gas that is collected over water. Okay, that should ring some bells or put up some flags for you that this is the exact scenario that we are talking about. The volume of gas collected is 0.25 liters at 26 degrees Celsius and 765 torr of total pressure. So this is P total. pH2O at this temperature is 25 torr. So here's the nice thing about vapor pressure of water. anytime you have water that establishes a vapor pressure, the vapor pressure that water establishes is extremely consistent. It will change as you change temperature, but it's extremely consistent for each individual temperature. And so studies have been done and calibrated and averaged and published. So these are things you can look up. If you go on Google right now and you just Google, what is the partial pressure of water at 35 degrees Celsius? Boom, it's going to give you an answer because this stuff has been cataloged. So the nice thing is you don't have to figure out both partial pressures. One can be looked up. The partial pressure of water can be looked up. And then you only have to worry about the partial pressure of the gas that you're producing. Okay, so that's why they give you partial pressure of water, because it is in a book and you can look it up. How many moles of O2 are collected? All right, so we have PV equals nRT. We have pressure total. We have volume total, we have R and T total, which means we can find N of what? N total. If we figure out pressure of oxygen, we have the volume, because the volume of oxygen is the same as the volume total. We have R, of course. We have T for all of it. We can figure out N of just oxygen. So again, there's multiple ways we're going to figure this out. I'm going to use the partial formula because it's faster for me. All right, so we want moles of O2. We're going to take PV over RT, solve for moles of O2, and we want to be careful we're using the pressure of oxygen. So that's 765 torr. So pressure total equals pressure of oxygen plus pressure of water. Okay, so if we take the pressure total and we subtract off the pressure of water, it's going to give us pressure of oxygen. 740 torr. All right, I'm going to convert that into atmospheres divided by 760. So 0.973, oh boy, 68, let's stop there, torr. Volume 0.25 liters, R 0.08206. Temperature 26 plus 273 is 299. Plug and chug. Okay, so I have produced 0.00992. Can I keep 3 sig figs? Looks like it. Moles of oxygen. Chana. All right, how many grams of KClO3 were decomposed? So 0.0992 moles of oxygen. We want to go moles of O2 to moles KClO3. moles of KClO3 to grams of KClO3, because that's what they're asking us for. KClO3 to oxygen is a 2 to 3. And now we need to figure out the molar mass of KClO3. Give me a second to do that. Okay, that would be 122.55 times 2 times 122.55 divided by 3. Let's bring it up here. 0.8105 is what I got. So I can keep 3 sig figs, 0.811 grams KClO3. Okay, who beat me there? So the nice thing about these problems is they're super straightforward. There's only so many ways they can kind of mess with this equation or this kind of problem. And usually when you see it on the test, it's very straightforward. It's pretty obvious. It's a collection over water, and you really proceed through it the same way every time. So practice this one until the concepts click, until you master the math behind it. And then you can walk forward really confident in this question. There it is on a test. We'll do that one together. All right, we have just a couple more concepts to go through. These are like the nitty-gritty details of gas law, the gases chapter. We've really gone through the bulk of the concepts. The bulk of the skills we've definitely gone through. These are the little details that sometimes show up. Kinetic molecular theory, though, is pretty huge. So let's talk about this. This is the why behind ideal gas laws. Why does it work? And so there's 5 different postulates that really make this equation work. The first one is that any body of gas consists of a really large number of molecules, and this really large, like almost impossible to conceptually grasp, it's that large number of molecules. It's always in continuous random motion. And so if there was one molecule, it would hit this wall, it would hit this wall, and your force would be unevenly distributed. But because there's so many molecules, they're in continuous random motion, you really get this like equal pressure, equal motion, average temperature occurring. Postulate number 2 is the volume of the molecules themselves, the protons, neutrons, and electrons that make up the molecules, is negligible compared to the space. So we kind of talked about this in the beginning of the chapter, but gases, a lot of their properties occur because the molecules are way too far apart. There's so much space there between gas molecules that they're so far apart, they don't even interact with each other, So that's why they're going to form a homogeneous mixture, whether you mix polar things with polar things or polar things with nonpolar things or nonpolar with nonpolar. The interactions don't matter. There's so much space compared to the volume. That's just one example of why this matters. Following that, we just stated this actually. Therefore, attractive and repulsive forces between the gas molecules are also negligible. They can be ignored. We can treat them as if they basically don't exist. They're too far apart. They really don't make a difference. Energy can be transferred between molecules that collide. Think of a pool ball. If all the motion energy of one is passed into the other, it will keep moving at the same speed. So it can be transferred during collisions, but the average kinetic energy of molecules, measured by the temperature, doesn't change with time. If it does change because you're heating it or something like that, the temperature is going to go up or down, depending on how you're manipulating this. but there is an average kinetic energy of the gas body as a whole, which may be different than the kinetic energy of each individual molecule. But again, there's so many molecules that it averages out and it acts like a body of gas instead of acting like individual molecules. Okay. Kinetic energy, which is that funky looking E, kinetic energy is proportional to temperature at any given time, at any given temperature. And the molecules of all the gases have the same kinetic energy. And so this is kind of what we talked about before. Temperature really is a measurement of kinetic energy or the motion of the molecules. If your temperature goes up, your kinetic energy of the molecules goes up with it. All right, so using the kinetic molecular theory, we can use it to help us understand pressure, understand temperature. We can help it to help us understand pressure by imagining pressure as a force that occurs because the molecules are colliding with the walls. So you can think of like gas inside this room as constantly colliding with the walls. If we sucked out all the gas all of a sudden and left a vacuum in this wall, that force pushing against the walls would be gone and our walls would just collapse in on us. So we can understand pressure as collisions with the walls. If we increase those collisions or we increase the strength of those collisions, we're going to increase pressure. We can also use the kinetic molecular theory to understand temperature because temperature is a measure of the motion. And as we increase temperature, we increase the motion of molecules also. This is a pretty important graph. This one shows up a lot on the test. And what you can observe off of this graph is that, notice it's a difference between a cooler sample and a warmer sample. And so a warmer sample has a higher average kinetic energy. A colder sample has a lower average kinetic energy. That makes sense. But there's another thing that we can observe off of this, and that is that the warmer sample, actually less molecules here are at that average. It's more evenly distributed between like faster and slower molecules, whereas the colder sample has more molecules at that average. It's less evenly distributed. Okay, and we're going to kind of get into the details about speed, effusion and diffusion. We'll talk about those in one more video. So good job, you guys. I'll see you in class.